2, 1. Go ahead.
All right, welcome everyone to today's episode of the Professional Development Seminar here at UAA. My name is Dr. Scott Hamill. I am the Chair of Civil Engineering and I will be your host today. Today we have Dr. Polly Murray, who is a postdoctoral research associate.
I don't know.
That's the correct title, I think. Postdoctoral research associate here at UAA. And we'll be talking about seismic safety in Puerto Rico, which is an interesting case study, particularly because it pertains, the construction in Puerto Rico is similar to most of the world outside of the US. So if you live in South America, in Asia, parts of Europe, then you'll see a lot of this. I will announce our password for the PDHs at the end. Yeah, I think that's it. So without further ado, Dr. Murray.
Thanks. So this was a project that was part of my PhD work at the University of Colorado Boulder, and we submitted a paper, and actually, very excitingly, it was just selected as the editor's choice for the most recent edition of the journal. And unfortunately, we've seen a lot of parallels between the work we did here and in Turkey, and the sort of, I don't know if it's a silver lining, but in Puerto Rico, there were almost no fatalities because there was one heart attack during this earthquake sequence in early 2020. Generally, people knew that their houses were unsafe, and there were foreshocks that we didn't know they were foreshocks at the time, but that people were aware of earthquakes. They were sleeping outside in cars, things like that. Obviously, the warmer weather makes that a little more peaceful. So it's sort of an interesting thing to be like looking at a community that's just had their town devastated and be like, well, this is a cool project. And actually, we started this project before the earthquakes happened, but it did give us a lot of insight into how these buildings were built and how we might make them safer in the future. So more than half, there's estimates between 50 and 90%, but at least half of houses in Puerto Rico are built informally. A lot of them look like this. And what we call informal construction is a non-engineered design, often with low quality materials because that's what's affordable or just what's available. They don't use standard construction methods, and they are often expanded incrementally. So you can see that the first story of this house was existing, and then additional stories are going up. Also in Puerto Rico, reinforced concrete construction with masonry block typically is very common, in part because the materials are readily available and relatively inexpensive, and they also do very well in hurricanes, especially because of the concrete roofs. Puerto Rico, as you probably are familiar, has many frequent severe hurricanes, and so you may not be able to have a wood frame house insured. It might get damaged, and so while there are things you can do in a wood house to make it more resilient to earthquakes or to hurricanes, concrete is generally the preferred construction method. So in January, or starting in December of 2019, but primarily in January 2020, there was a series of earthquakes, the largest of which was a magnitude 6.4. And it led to the collapse of lots of these soft story houses where the first story is more open. We'll get into that more. And we saw lots of cracking in masonry walls, things like that. So these are both in a town called Guanica, which is on the southwest side of the island. And that's where we saw the majority of the damage. So because we're researchers, we had to develop a framework to do this assessment. And the goal, and we've seen it play out in Colombia too, is that we can come up with a set of steps that you can follow, and then you can apply them to the specific building archetypes in a different region. So it's sort of guided by these questions. So how does informal construction affect the earthquake risk of houses? What building characteristics most influence your seismic performance? And then, of course, what improvements do we make to houses, both while we're building them and to existing structures to reduce that collapse risk? So the first step was to interview builders, hardware store workers, and visit the earthquake affected area. We also interviewed homeowners about their motivations and what they look for in a builder, things like that. And so again, I mentioned we had planned this project before these earthquakes happened, but these earthquakes happened. But then we happened to be there a month after the earthquakes in February of 2020. So on that visit, we sort of identified two very common house archetypes, and then this is what we focused on in the study. So on the right, this white and pink house is an open ground story house. And if you look closely, you can see it's not where it began its life. And there are really, really slender columns supporting a rigid lumped mass in the form of that upper story of the house. So this is a great design for flooding. If your town floods regularly and you have 5 feet of water, all of your things are going to be fine. It provides nice shaded parking. But this is a pretty extreme example of the soft story and weak story that we see in all over the place, but especially in Puerto Rico. The other is sort of the standard masonry wall house. They're generally rectangular in plan. We'll talk more about these archetypes and how we model them. We spent a lot of time at hardware stores chatting with people about, what are people buying? What questions are they asking? What are they worried about? And it was a really interesting, it's very cool to have these conversations and have people talk about what they stock up on when a hurricane's coming and how people's thoughts have changed just in the month since those earthquakes hit and what they're prioritizing. And so just talking about some of what's available, a lot of the rebar is stored outside, and of course it's rusty and corroded. The transverse ties, this is sort of a selection of what's available, and we use this to kind of guide our assessment on what people are, how columns are designed. It's sort of like, well, these are the ties that I can buy, so this is the column size I'm going to use, rather than this is the column size I need, and so let me form ties to fit that. The concrete masonry blocks, we saw a wide range of quality here, and the simplest way to test the quality is to hold it out in front of you, ideally not wearing flip-flops, and just drop it to the ground and see what happens. If the block doesn't break, it's probably pretty good, and if it does shatter, then probably not that good. And we shattered a lot of blocks while we were there, but we also didn't shatter a lot, so hard to know what you're going to get. There's not really a designation. The cement is pretty standard, Portland cement. We saw both river and beach sand. So beach sand, of course, has a higher salt content, which is not so great for your already rusty rebar. And the coarse aggregate was just bags of rock. So even at the sort of nicer hardware stores, there's not always access to the higher quality materials that an engineered design might call for. So,
Do people know that beach sand is?
I mean, no contractor would tell us they use beach sand, but it's.
So they know.
Yeah, I think they know. We asked a lot of contractors, like, do you build the frame first and then put the blocks in, or do you put the blocks first and then frame it? And with certainty, every person, we had about a 50-50 split on which was the correct way to build. And those who know, there is one way that is better to build than the other. And so there's a lot of sort of passed down knowledge and not formal training. And so people are told, yeah, frame first, then put the blocks in, and they think like, yeah, that's got to be the best way to do it. And that is literally not the best way to do it. So we categorize these different vulnerabilities, particularly those slender columns, and it's a little bit hard to see, but the tie spacing in this column, this is that house that I had that collapsed on the first slide. The tie spacing is really large because I think a lot of people think it's just there to hold the rebar in place while you pour the concrete, and they don't realize the importance of those ties for the shear strength of your column. And so generally we saw really questionable columns, lots of weak or damaged materials, and these vulnerable building configurations. So the soft stories and the infill masonry walls. So the next step was to take this information and build computational models in software called OpenSeas, which is the open system for earthquake engineering simulation. So this lets us build nonlinear numerical models that we can then use for dynamic analysis. So in general, we looked at 1- and 2-story masonry block houses. These have thick concrete roofs and are generally pretty regular in plan. They almost all had this corner cutout porch thing. Great. And as an aside, when we were walking around, people were offering us water, and it was one of the most I felt very welcomed. I sort of wish I'd had some kind of official looking vest, because we were just basically other tourists walking around with cameras taking pictures of the damage. But once people found out we were engineers, they were like giving us water and food, and a lot of people were sitting out on their porches. And it's a lovely day. So
were you part of any official team, or are you just going as a researcher?
Just going as a researcher. We talked with the folks at ERI, which is the Earthquake Engineering Research Institute, a bit, and coordinated with them. But we were sort of our.
Was it part of any research project, or it's just out of your curiosity or for your?
Oh no, it was part of a project.
Okay.
But I think some kind of
Understand.
desk that just said we're not just white tourists coming in to look at the carnage would have been probably good.
Just engineer.
Just lessons learned for next time. So a quick review or introduction to masonry construction. So infill masonry, which is this left side, you build the concrete frame first, and then you add blocks in either at the time of construction or maybe down the road. And in this situation, the frame is load bearing and the blocks are considered non-structural. And they're often non-structural in design, even in places where there are building codes, things like that. But those blocks will affect how your columns perform, especially we'll get into the partial height infill, where you might have a short exposed column that will see large shear loads. In confined construction, you put the blocks in and then you sort of tie everything together with the beam and columns. And in this case, the whole system acts as a unit and it's much stronger. And this World Housing Encyclopedia is a great resource for how to improve confined construction or improve masonry construction. And the answer is always build confined. So in those walls, we ran this parametric study. We varied the concrete strength, the masonry strength, the method of construction, and the configuration of the wall, so with openings. So we looked at solid walls, walls with windows and doors, and then this is the partial height infill. This is a very common situation in schools because it allows for light and ventilation, but you still have privacy. And what happens is that, do I have to laser it on? Maybe, yes. No. Anyway, these short columns experience large shear loads, and they're not able to.
You might be able to right click to get to the pointer. I don't know.
Oh, pointer.
Or option click.
Right there. This section tends to be where we see failure in partial height infill.
You can also point to the screen because the camera's
Oh, yeah.
following you.
Okay. It's following me?
Magic.
Just a little bit. Not a bad way.
Weird. Okay. And so getting into the modeling here, this is sort of a cartoon of our OpenSeas model. And we have these trusses that are calibrated to represent the behavior of either the confined or the infill masonry wall, with what's called an IMK hinge that captures the rotation in the columns. We applied loads and a lumped mass at the top, and then fixed the base. So this is our model for a single wall, and then we put that into the full model, 2D model of the house. And this is an example of our backbone curves for confined and infill wall with otherwise similar process, same concrete strength, same masonry strength. The only difference would be how you built the wall. And these are from two separate studies. So the infill, which has been studied much more widely. It comes from a database developed by Huang et al. And equations developed by Bose et al. And you can see that our infill has a much more ductile backbone curve, which is surprising because infill is less ductile generally. And our confined masonry, while much stronger, is less ductile. And this is surprising. We didn't think this was right, but this was the best information we had at the time. So if anyone as a research project wants to test a bunch of confined concrete walls, that would be a great thing for the research community. But we spent a lot of time agonizing over that discrepancy. But both studies are sound. Yeah.
Could that be because the confined population includes those that have that clear story or whatever you call it above the top of infill?
So those would be considered infill because the confined has to act as a single unit, so you couldn't have the opening.
Regardless of the sequence of construction?
I think so.
Oh. Okay.
At least we always talk about partial height infill, and because with the confined, you're tying the whole unit together, so you couldn't have a gap at the top. I don't think.
I just wondered if the confined is penalized because of including that population with the partial height infill that's poor performing.
Yeah, that I think all the studies that included partial height were included in infill, and actually I don't think we used a separate calibration for the partial height. So anyway, the challenges with numerical model, that always doesn't feel great. So from there, we developed a sort of typical building plan, and we modeled one frame line of it that we determined to be like the critical frame line for the structure. And that looked something like this. So kind of capturing that front frame where you have an opening on one side. So we had 2 bays with masonry info on the second story, 1 bay on the first story. Relatively slender concrete columns and an 8-inch concrete slab. And we did vary the thickness of the slab in some of the models. That's a pretty big effect. So this is generally what our model looked like, sometimes without those struts on the right-hand side where you have a bare frame. We have applied loads, lumped masses, struts. I can get more into the modeling, but this is sort of a general overview of, I feel like this is not the most interesting part of the study. So then looking at the open ground story houses, we could simplify here because that upper story acts as a single rigid lump. And so these models looked like this. So we had a rigid beam with big heavy masses to represent that second story. I'm not sure you can even see it at all, but the column in the middle back there has just rebar for about this much of it with no concrete left. And post-earthquake, yeah. At some point, I have a zoomed in photo, I think, of that column. There was a PVC pipe down the middle of it. Cool. So in these, we were most concerned about the configuration of the columns. And so we varied the number and size of the longitudinal bars, so either 4 or 6. In general, we used all 8 by 14-inch columns, which are based on the ties that were popular in our first stories. We varied the transverse tie spacing from 2 inches, 6 inches, and 14 inches. We varied the concrete strength based on interviews with builders and how they told us they mix their concrete. And we added rebar corrosion to some of the models. And we also added a PVC pipe. So in this similar vein to the hurricane risk and rain and flooding, people had drainage off their roof, but they didn't want to look at a gutter, so they just put the gutter inside their columns, which took away a lot of the confined concrete in the center of that column, which alarmed us as we were walking around.
Did any of them have it in the middle?
Some of them, there is sort of like all over, but we put it here because it was the most
Worst spot.
worst spot. Yeah. And then in some cases, we looked at a retrofit option. So this is a reinforced concrete jacket where you add additional concrete and steel to the outside of the column to make it a bigger. In Puerto Rico and other places, incremental construction is very common. And so, and you know, like adding an addition to your house is not an unfamiliar concept, I think, to most people. But it's very, very common here. And what we see a lot is rebar left exposed up above the slab so that you can attach additional walls. And of course, if you leave rebar exposed in a salty, wet environment, it's going to be corroded. So we looked at what happens if you attach columns with like very rusty steel. And also you may have a set of blocks in your first story that are high quality and then your second story might be low quality or vice versa. So lots of variation in how things are built. And then you may also build a concrete first story and then add a wood second story on top. And this, we chatted with this homeowner for a long time, and he was very proud of this roof. And he had hurricane straps. I have my office, I should have brought in, but every like foot up here. And so it was, we were happy to see it because he had lost his roof in Hurricane Maria. So people are very aware, they're thinking about hurricanes. And I think generally people were not thinking about earthquakes until a few years ago. So we modeled incremental construction, varying the number of stories, adding rebar corrosion. Yeah, here's it looks like a totally finished house, and then there's just like sticks coming off the top. And so we captured that corroded rebar by basically making the columns at the base weaker. So we varied the parameters of those hinges. So the next step is to run incremental dynamic analysis, or IDA, with these models, and that lets us quantify the collapse risk. So has anyone here heard of or used IDA? Okay, great. So it's a process where you can run a bunch of ground motions on a computational model at increasing intensities, and then you can figure out what intensity will cause this building to collapse. And you can imagine, so each line here is a single ground motion record. And if you just run one ground motion and it collapses at 2.5 G, maybe that's your collapse capacity, or maybe that's the strongest it will ever be because the frequency content of that earthquake and your building jive in a way that your building manages to survive to a much higher intensity. Or you might run it and it only gets to 0.5 G. So that's why we run this set of ground motions. So each line is a ground motion record. We run until we hit the collapse threshold. So we measure our demand in terms of story drift, so how much your slab and your floor are laterally separated. For our open ground story houses, we use 5% story drift, and for our wall houses, we use 1.5. That's when they start to drop off in strength. It's a little bit confusing because typically you would have your input component on your x-axis and your output on your y-axis, but engineers like to see drift as a horizontal measure, and so we increase along the y-axis here, and we scale based on spectral acceleration at the period of the building. And so we increase along the y-axis the intensity of the earthquake, and then we measure our drift until we get unstable and we cross our collapse threshold. So we use, for most of the buildings, 22 different ground motion records that contain variation in duration and frequency content, and they are representative of a far field ground motion, so a ground motion that occurs, forget the exact distance, but sort of far away from the building it's affecting. And this is a FEMA set that's pretty widely used.
So the X represents the full ground motion from start to finish. So the full record of the ground motion from start to finish. And then the worst case drift experienced during that ground motion.
Yes, exactly.
And then you increase the intensity, and then you get another X.
So we did this for each building model each version that we looked at. And then we get a range of ground motion intensities that cause collapse. This is a slightly different structure. So this is one where the collapse threshold is 5% drift. And you can see that the range of collapse drifts goes from about 0.3 up to 1.1 G at the graded building. So not the strongest building that you want to be in here. And so we take that range and we fit a cumulative distribution function to quantify the probability of collapse. So now what we're looking at is, rather than the intensity of the earthquake on the y-axis, it's now down here on the x-axis. And as our intensity of earthquake increases, our probability of collapse increases from at a really small earthquake, very unlikely to collapse, at anything bigger than 1.2, sort of all but guaranteed to collapse. And so it's shown, that's what this curve is showing. The x's are an empirical probability, so you can count how many at, say, 0.65 G, how many of those records collapse the building, and in this case, that's about 50%. Sorry, I had the animations out of order here, but so that corresponds with about a 50% probability of collapse. And then we can compare that to the MCE, or maximum considered earthquake intensity for Puerto Rico. And we present it as a range because it's sort of the range of values across the island. And so for context, when you're looking at a plot like this, in the MCE range of the island, this building has a 25% probability of collapse. But actually not the worst one that we've seen. And so that we can compare using IDA, or using those collapse probabilities that we developed from IDA, how well different buildings do in comparison with each other. So this is the IDA curves for infilled and a confined masonry building. So that's the only difference between those two buildings. And if we, this one away, if we look at how at the earthquake intensity at which these two curves hit the collapse threshold, you can see that generally the confined are reaching a higher intensity earthquake than the infilled. And that shows up here too, where we can see that in our MCE intensity earthquake, our confined masonry building is much less likely to collapse than our infilled masonry building. Question. This is all the results are shown in this format, so if you have questions now. Cool, great. So from there, we can quantify our collapse risk of different parameters.
Can you go back to
Yeah.
So the graph on the right is saying that the gray part is the typical intensity for Puerto Rico.
MC, yeah.
Okay, MC. So you're basically saying that for a typical building in Puerto Rico, as you modeled it, shown, the probability of collapse for an infill is about 50%.
In an MC, yeah.
And the probability of collapse for a confined is about 4%. Meaning 87% of the buildings will survive.
I mean, yeah.
I'm just making sure I get the problem the right way.
Oh, yeah, yeah. So it.
Meaning the probability of survivability. Sometimes it's shown the probability of survival.
Oh, yeah.
Probability of survival is higher for confined.
Yes. So basically, the further right and the further down, better performing. Hopefully the slide titles. This is a big thing in our research group, that your slide title should just be, if you don't pay attention to anything else, like that's what you should take away from the slide. So, so no surprises, generally, that confined construction is better than infill. And we looked at both 1-story and 2-story houses. So the 1-story houses are, I should have done this in the thought anyway. 1-story houses are purple and the dashed lines are infilled. And so 2-story infilled is here, not so great. 1-story infilled, okay. 2-story confined is okay, maybe not ideal in a big earthquake. 1-story infilled and 1-story confined, not a huge collapse risk. So closer tie spacing and additional longitudinal bars decreases your collapse risk. And generally, these buildings that open story, it's really hard to have enough in an 8x14 column to support that building in an MC level event. One more thing. So in general, these were shear critical columns, so they have brittle failure modes. So if we increase or decrease the tie spacing, so we have more transverse ties, our deformation capacity increases, and if we increase the number of longitudinal bars, that increases the strength of our columns. So both good things. This one is, I think, really surprising that stronger materials can reduce your collapse risk, but perhaps not the most important feature. So on the left, we varied the strength of our masonry blocks. So that was, I guess, based on how they advertise it, and then also what happened when they dropped them. And that's part of using this range of values. So if you have strong masonry block and mortar and the whole thing, less likely to collapse than if you use weak blocks and weak mortar. Similarly, in the columns, if you have stronger concrete, you're slightly less likely to collapse, but the steel really makes more of a difference in those. Partial height infill is bad. So these have, you can see that it shoots straight up to basically 100% chance of collapse very early. So we saw you don't see a ton of residential structures with partial height infill, but they're really popular in schools. And then you can see that sort of pancaking effect. And again, unfortunately, this earthquake happened, I think, on a Sunday. And so schools collapsed, but there were no students in them. But it's been a very bad situation. And so, again, these are the shear critical columns that we are trying to apply. This finding was surprising to me, and I want to test it. But we didn't find that the PVC cutter made that much of a difference. Basically, based on where it is in the column, and that the concrete didn't matter as much as the steel in general, we basically couldn't come up with a model that made it matter that much. And this has been found. Other people have studied what happens if you put a PVC pipe in a concrete beam, and they were like, oh, it didn't matter that much. My gut tells me that it should matter, and so I do want to test this, but maybe share. Well, so if we have corroded steel in those open ground story columns, so we basically just weaken the steel, weaken the bond with the concrete, that will increase your collapse risk. But it actually was not that much of a problem in those incrementally constructed houses where the rebar is left to rest. And perhaps not surprisingly, the heavy second story really increases your collapse risk. So I don't know if this is why people were opting to build the split, but it was a good decision, because rather than having a large mass now on top of your potentially weak columns and walls, now you have a pretty lightweight structure on top. So this configuration where you have a wood second story on top of a concrete masonry first story is very popular and pretty good for earthquakes. We also looked at retrofit. So we compared an unretrofit building to one with a reinforced concrete jacket, and we looked at 2 different sizes. And then we looked at infilling a single bay versus 2 bays. And obviously, if somebody has that story open, they probably have it open for a reason. Maybe it's where they park the car, maybe it's for flooding. So it's a little silly to be like, yeah, just add walls to your house and then you'll be fine. It changes the functionality of the house. So we looked at a number of different options that all reduce risk, basically infill or a big beefy reinforced concrete jacket will reduce the risk the most. So in the summer, let's see, I have it. And this little animation for my defense. Cool. So this is all of the models that we looked at on one figure. So open ground story houses, almost universally high collapse risk in the MC level event. Partial height infill is in green here, even worse. Infill construction, generally more vulnerable than confined construction, generally better than the open ground story houses, and the dashed lines are 1 story versus the solid lines are 2 story. And then, but anyway, combined better than infill 1 story or 1 story with wood on top, better than 2 stories. So from here, we came up with a set of recommendations. So generally opting for lighter construction, including thinner slabs. And I didn't put the slide on here because it felt a little in the weeds. But when you have concrete, if you have an additional load, to some extent, you get additional strength. And so in theory, you have more weight, then you have higher flexural strength. But that did not outweigh the additional seismic mass that was then moving around. So don't go too thin because then you have hurricanes problem. But generally, you don't need to put thick concrete slab. Confined construction is the way to go when you're building with masonry, as is just avoiding those open ground story construction, or if you really want that, designing those columns for the large lateral loads. Retrofit of existing open stories with either infill or reinforced concrete jackets can be effective, and using uncorroded steel reinforcement, adequate longitudinal bars, additional ties, and stronger blocks, if you can find them, is an effective way to increase your strength, reduce your risk, and always avoid partial height infill. And generally, when expanding, go horizontally if you can, or vertically using wood. So this was a group effort with this project team. So Abby Lau, who's my grad school advisor, Orlando Arroyo, Amy Jevernick-Will, Briar Goldwyn, just attended a few months ago, and Dursa Feliciano, who's been working on a similar project in Colombia with Orlando. And we had a really great research team down in Puerto Rico with Nicole Ramos, Urias Gonzalez, and Junelis Olivares. Cool. Any questions?
Could you remind us what the intensity,
Of an MC?
yeah, and like kind of what distance, and especially like what the actual earthquake was in terms of magnitude?
That's a great question. I don't know if so the MCE depends on the period. So those who may have forgotten, this is your SA, which is G, and then this is your period in seconds. And so this is your PGA here. And you have a curve that looks like this, kind of, if you're in pre-2022. When did AXC 17? So that's why when I specify spectral acceleration, I say the period that we're measuring it at, because if this, our 1 second, or 0.1 second is up here, so the block walls are much stiffer, and then our 0.8 might be somewhere out here. So the intensity of those is very different in how the building responds.
But what's the peak?
And I don't remember what the peak meant. So I just figured I'd answer a different question, and then I don't remember
Was
what
it 2020?
Yeah. There you go. Yeah. Great.
And you said there were several significant aftershocks to that.
Yeah, so there was a 5.8, I I think the day before or 2 days before, and that one toppled like a pool of rock that was kind of a tourist attraction, or an arch maybe, and that went down in the 5.8, and then it was like the next day there was a 6.4. So
actually went up.
yeah, it got more intense, which is a pretty common, and we don't know if things are going to be foreshocks until there's a bigger earthquake after. The largest was a 6.4.
It's always hard to find.
Focused right
Yeah, it is.
on the.
Oh,
island
because you
too.
search like USGS Puerto Rico earthquake, and then it gives you news about it, which is helpful, but so I think it was not an MC level event. I think it was like 60% of MC, so it'd be, somewhere in here or here.
And MC, that is the median too.
Maximum
Maximum,
considered.
maximum.
So
Maximum considered.
Maximum
this
considered.
would be your MCE. And then your design level is, that's not how you're calculating it, but is 2/3 of it. And so, yeah, they're both good measures, and typically you have a different metric that you're trying to reach for an MC or a design level event. So you might have collapse, like you might not want to see anything above 2% drift in a design level, but 3% drift is okay in an MC based on your.
I'm not yet. Did you do anything with, 2 questions, did you do anything with the strength of the steel?
I think we did use 2 different steel. Maybe not, because I don't think I put it on the slide. We may have just done,
You mentioned varying the steel strength in your presentation.
Oh. yes,
I can't remember if it was strength or layout.
I think we did very strength. Yeah, because I think we did 60 and 40. Yeah.
Because one of the things that I found in the Caribbean is that you have 40 and 60, and there's no way to tell the difference.
Yeah.
Which is kind of funny, right? There's no, like, you can't look at the bar and be like, this is 40 or 60. Like, the only way we were able to tell the difference was actually by bringing it back and testing it. So,
Which, if you're a homeowner, like, how are we gonna know?
yeah, right.
In terms of non-destructive.
Yeah, there's no way.
Yeah,
no
that
way
too,
to
yeah.
do it. Okay.
Well, and even destructively, there's no way to do that on site, right? You can't even cut a piece off, and like, who would do that? We
I'd like to cut a chunk out of your wall, please.
Yeah.
I mean,
Or, well, even
Yeah.
even in the construction yard, right? Like, you buy a 30-foot piece of rebar, you could cut a 12-inch piece off and bring it back and pull it apart in the lab. But nobody has a lab in
yeah,
Puerto Rico.
well, I mean,
There's
the
one, yeah,
university,
but
but
the point is,
yeah.
like, there's no way to know, and some people are selling 60 and some people are selling 40, and nobody knows. So, my other question was, did you do anything with, was everything 2D? Okay, so you didn't look at, like, if you have an L shape and plan.
Yeah, because we wanted to run, I forget how many analyses it ended up being, but it was the computational time, and because most of the buildings were rectangular, we stuck with 2D. But there were a lot of houses, I don't know if I could pull up a picture, but on a hillside, 4 or 5 stories, where some of the stories were just columns, and then some of the stories were masonry. And we were just walking around one day, it was great, and we interviewed the guy that owned that house, and then it turned out his mom lived across the street, and she had a 1-story with like maybe a small wood addition, and she was like, oh yeah, he's scared, so he's been sleeping over here, and he's like, the house I think would have done this, but the earthquake didn't. It was not the part of the island that was most affected by the earthquake, so. Yeah.
You mentioned computational time.
Yeah.
What sort of hardware, what sort of computing power are you talking here? I'm in the water and wastewater, so this is
Oh, yeah.
unfamiliar, and this is a lot came and gone a long time ago.
I was using just kind of a beefy desktop, but it had 20 cores, so I could run a bunch of analyses at once, and basically each, when we look at,
Yeah, are we talking your MacBook, or are we talking?
No, I had
Deep
a
blue.
desktop. So when you run,
Then you can run one on.
yeah, you can, yeah. And each X takes anywhere between 12 hours and 10 seconds. So with these, they were generally pretty fast. Once you get into the unstable zone, they take a little longer. But we could run 20 ground motions at a time. So it would run one intensity and then make the earthquake bigger, run the next one. But we had about 400 to 500 analyses for each building, and I think 30 buildings. So that is why we not go with the. Although I think that there is a lot of value in doing 3D modeling. But,
So how much is just pure computational time?
oh, I don't know. And I reran a lot of stuff, and I don't know, many hours. A lot of it was like I would start some stuff running and then work on some other things. My whole life. It was fun. It was good. Worth it, maybe. Are there any questions?
Andy. No.
I'll go put it in chat. Any other questions?
No. Just gonna see if I can find
Oh, the.
the PGA. You should know.
I should know.
You should know.
I did know. And so. This was our paper.
Well, you had the range.
Hmm?
You had the range. But those are in your,
Oh, that's the design.
that's design.
Yeah.
Yeah.
And at some point we had another line for what that was.
At a particular period.
So did people actually do something? Okay. Most intense shaking was a PGA of 0.5. Should I just read this aloud? It's only we don't need to pay $600 since we were so over the page.
Is it 0.5?
0.5 G.
Okay.
Yeah. But that was PGA.
Oh, yeah.
So are people down there in Puerto Rico actually going to do something with your research?
I hope so. So Friar Goldwyn, who's on here, did the kind of community social science side of it. And she has been working both before in developing like or identifying common house plans and things, and now in disseminating the information. And so we did some interviews with people who host workshops for builders, so sort of like the one that we had here. So she's been kind of coordinating that. So taking this, and there was a concurrent study about hurricanes and winds and wood houses, and packaging that up into information that's helpful to other people. That's a great question because it's
So people that have a home or a building that is susceptible to collapse, did your research cover helping them identify their building is susceptible to collapse, and then maybe things to retrofit it to make it so that it's stronger?
so we have sort of a table of recommendations. I don't remember exactly the form, but it was like if you have an open ground story house, consider doing this. But it's hard to know how strong your blocks are without like taking one out. And so it's so We didn't get into too much detail. There's a retrofit guide that a professor down there has developed that's like, if you have an open ground story, here's some options.
Oh,
And this sort of just provided numbers for how that would affect your collapse risk. So there's some helpful like home building documents, I guess, where people have lots of information about steps to take to build your house and what to look for in materials. And when we met with people, they said that there was a lot more interest in safer construction for earthquakes following the 2020 earthquakes. So the hope is that we can provide information there rather than trying to create our own way to tell people what to do.
are you gonna go to Turkey?
I don't know. I have not. Some of my like grad school friends and stuff have been out there, but may do some work with it and see. But yeah, there's a STEER, which is structural earthquake engineering reconnaissance, and GEAR, which is geotechnical, and they usually deploy pretty big teams like right away. So be interested to see more. And I'm going to a conference in a month, and they've added a special session about Turkey.
Do you know if they have similar construction?
We've seen a lot of the same, like really large tie spacing and open ground stories. And so, you know,
Yeah, I've seen that too, but like,
Yeah.
do they, I haven't been looking for infill, like I haven't been looking for masonry, because they have a lot of like concrete framing.
yeah, I think there is a lot of infill.
Small stuff.
And they had some earthquakes years ago, and the infill construction was a problem then too. So it's been a problem. And most of the stuff that I've seen has been the really big buildings, so I don't know how much of this 2- and 3-story residential stuff has collapsed, but I'm sure it will be evident soon.
The last sentence in your bio says your current work is taking you wood frame houses built out of compliance with local code. Is that like Alaska local code? Or
Yeah.
Have you spent time looking at 2018 and the building safety zone and stuff like that, or?
Yeah, that's a project that I was hired for.
Very cool.
And so we have tested a bunch of these walls that are out of compliance, because like the confined and infill masonry, there's a fair amount of testing of infill construction, but we don't always know what happens when people build confined, but maybe without materials, things like that. And so similar, we don't always know what happens if people don't put any nails in their mud sill, or they just have one row of nails in their T111. So we've been doing a bunch of testing in the lab to get these backbone curves, and then we can calibrate the models rather than relying on someone's master's thesis from UBC in 2009. Just the only person that's looked at confined construction. Did you also have it?
Here's the
Uh,
PGA,
oh yeah,
so it's like 25 sales center,
yeah.
and then like, 0.3, 0.2, kind of 20 kilometers out. So for reference, the
So not-
2018 earthquake was like, if you were in a really bad spot of town, it was like 0.4, I think.
And you were saying 2018 here?
Yeah.
Okay, gotcha.
So their shaking was, 20 to 30% more in terms of acceleration at ours, even though it's magnitude.
What about the duration of that too?
I don't know what theirs was. Ours was short.
Yeah, that's
It
what
was
I remember.
not as short, but
I remember hearing speculation that it was much longer at that intensity that we would have seen much.
Yeah. True.
yeah.
And also the the accelerations in Anchorage in 2018 ranged from 0.1 to 0.35, 0.4, because Anchorage has a very
The lithology.
the soil and geology is such that it's all over the map, depending on where you are. It can be worse or better. But in Puerto Rico, according to this map, it's pretty much like, 0.5 Gs around the fault and then 0.4 and then 0.2. So I imagine you guys could probably tell the damage as you went away from that.
Oh, yeah.
Yeah.
And we went to Ponce, which is more of a like tourist, older, historic district. It was like, oh, look at that big crack. And we drove a couple hours down to Quantico.
You said it was centered offshore too?
It was at the coast.
Yeah, it was
Right on the
Rico,
coast.
yeah. Sorry.
Scott, the values you just mentioned though, for Anchorage, those are peak ground motion values, aren't they?
Right.
The spectral values approach 1G in some structures, where there was instrumentation.
Here, I did not see anything that approached 1G.
But amplified, and you can multiply by 5, where you go. For a spectral.
Why are you
communication.
multiplying by?
Pardon me?
Why are you multiplying by?
That's the spectral amplification factor for acceleration
Well,
between ground motion and peak spectral.
I knew you were gonna look at me. As a design value
it's not.
or,
Yeah.
Well, if you compare any design spectra, the zero period value is 0.4 times the peak.
That's
What
the
it's five.
design, that's how the
Yeah.
design spectral is set up, yeah. But
Right.
that's this,
Yeah, that's that,
yeah.
yeah,
Right,
but the reason. Actual shaking, that's not generally how it works. Usually the peak can be anywhere in there, right? So the peak doesn't necessarily happen.
Well, there's also the peak that of the ground motion versus the peak that the building experiences.
Well, those are different too,
Yeah.
yeah.
But typically, a ground motion will have the frequency content of the ground motion will be something like
Yeah,
this.
right.
So
Well,
you're,
suggestion is we can't compare peak ground motion values with peak spectral. values.
True,
Right,
yeah, that's
yes,
true,
yeah.
yeah.
And it sounds
I'd be
like you're
I'm
getting
curious
it.
about.
No, I was comparing peak to peak, like PGA Puerto Rico to PGA. That's what I thought.
But, yeah.
These
Data
are all
with
different
spectral.
flavors of apples.
Yeah, we use spectral acceleration because it's relevant to the period of the building. But I don't know, you can get PSA,
Yeah, it's harder, it's hard enough to find.
yeah, I know, it's hard.
It takes
I'm-
an hour of digging to find something.
Yeah.
Our original question was whether or not both the confined masonry and the unconfined, or no, infill masonry were all grouted masonry.
We assumed that they were, because we saw some. just
So
blocks.
how do they keep the grout out of the masonry when they pour over the top of it?
That's a good question. I don't know if we saw.
I've seen, like, they stuff newspapers.
I know what we do.
Yeah,
I didn't know what they did.
Yeah,
that's what I saw.
that's a good question.
They'll just stuff down there.
We asked people like,
How
oh,
do you
what
keep that
what
out?
order
Who
to do
doesn't
it,
that
but
operation?
we didn't ask, yeah.
Locally, it's all sorts of stuff from expanded metal to fiberglass, blanket material to blanket stuff.
We also saw, you can buy this horizontal bed joint reinforcement. And
yeah.
basically everyone we talked to was like, nah, it's too expensive, you don't need it. So, there's some things people could be doing differently.
Okay, well, that's about
Thank you.
out of time. So, thanks, everybody. Great questions. So the PDH code is concrete.
Yeah.
Yeah,
Did
so,
you choose that?
no. No. But yeah, so if you go to the website, type in your information and type in concrete and spell it correctly, then you will get your PDH certificate to download. So.
And if you type in cement, you think they're the same, you get negative.
You get
points.
you get negative.
I was
Yeah.
waiting for
That's right.
someone to make the cement joke.
You have to come in for an hour class.
Yes.
Yeah. So,
Thank you very much.
thank you.